Hey everyone, welcome back to Calculus 1. This will be lecture 3. In this lecture we're going to talk about how to evaluate limits analytically. So we'll get into a bunch of very nice, very convenient theorems that'll help us evaluate limits in a more efficient way than we had previously. Previously, if you recall in the last lecture, we talked about evaluating limits numerically, right? So plug in a bunch of values that get ever closer to the limit point. And that while that works and generates good intuition, it's not very efficient. The other method we used last time was identifying limits graphically, so like graphing the function and taking a look at visually what happens with the values as you approach the limit point. And that's another example of a way to do it, but it's, aside from generating intuition, it's not the most efficient way. So we'll get into some more efficient means today. Now this lecture is going to be relatively longer, so what I'll likely do is break it up into 2 parts just to keep the video a reasonable length. Okay, so let's go ahead and get started here. Let me back this up just a little bit here, zoom it out just a little bit. There we go. Focus. All right. So this will be section 1.3, and we're going to be talking about evaluating limits, and specifically analytically. Okay, so what we'll do is let's go ahead and start with just the simplest theorem. This is really the first theorem to start with. So we'll be doing the most basic kinds of functions. So let's go ahead and let b and c be real numbers, and let n be any positive integer. Okay, i.e. a whole number, a real counting number, whole number, or 0. Okay, then the following. So the limit as x approaches c, the limit point of a function b, where b is just a constant, of course that limit's just the constant, right? Very easy, very obvious. The limit as x approaches c of x is c, okay, right? So if the function is a simple identity function, then the limit is equal to the value of the limit point. And then 3, the limit as x approaches c of x to the n is just equal to c to the n. Okay. All right, so very straightforward, very simple theorems, right? So these are arguably like the simplest kinds of functions you can deal with. Now, clearly, a function that is a constant, that's going to have a constant value, right? And it's obviously going to have that same value for any value in the domain, which would be all real numbers. And then this is an example of the identity function x, y equals x. And so clearly that's a function with no gaps, no holes. There's no reason for the limit to ever be anything other than the value of the limit point. And finally this one, so x to the n power. So any power function here is has a simple limit as well. Okay, so now clearly these are very simple, but what we'll do is we'll use this theorem to build up more complex and more interesting functions. You could probably see, or potentially you can imagine how it might be the case that we could identify limits of basically any polynomials using this theorem as sort of the backdrop for that, or sort of the mechanism. Okay, we won't prove all 3 of these just because it's time consuming and not really that helpful, but let's go ahead and prove item 2 here. Let's prove this one. And to prove it, we can use, we're going to use epsilon delta, right? So when you're talking about something super foundational like this, you probably have to use epsilon delta. But once we've proven these three theorems, or once we established this theorem is true, we may be able to use this theorem in place of epsilon delta for other types of functions. And so let's take a look at the proof here. So as we saw before, let's let epsilon greater than 0 be given. Okay, and then let's go ahead and choose delta equal to epsilon. Okay. All right. So then, well, then let's assume that 0 is less than x minus c, which is less than delta. Okay. And we'll just need to show then that the value of the function f of x minus the limit c is less than epsilon. Well, that's obviously true, right? So if x minus c is less than delta, then we have f of x minus, well, let's put the limit in there just to be really crystal, right? So f of x minus L, which is of course equal to, in this case, x minus c. Okay. All right. So the function f of x is just x in this case, right? So, and then the limit point, what we're saying the limit is c, right? So x minus c. Now, obviously, the absolute value of x minus c is less than delta by assumption here. So that's less than delta, and we set delta equal to epsilon. All right, so any epsilon you give me, I can find a delta, namely delta equal to epsilon, such that the value of the function and the limit are within epsilon of one another. All right, so that's like a pretty clear and simple. That's about as simple as an epsilon delta proof would ever get. Right, now you can do something similar for these other ones. The constant value is very trivial. This one might be a little more involved, but I would recommend giving it a try if you feel so inclined. Let's take a look at an example just to make sure that we're clear on what we're talking about here. Very simple, right? So this is basically saying that the limit as x approaches 2, for example, of the function 3. Well, what's that equal to? It's equal to 3, right? The value of the function is always 3. And so obviously, even as you get infinitely close to the value of x equals 2, the value of the function remains 3. There's no holes, no gaps, no discontinuities to be concerned about. So that's all good. The limit as x approaches -4 of the function x. What's that limit equal to? Well, this is the identity function up top here. We talked about that. It's equal to basically the function evaluated at c, or conversely, if you want to think about it as being equal to the limit point. So in this case, it's equal to -4. All right. The limit as x approaches 2 of x squared. So this would be an x to the n, where n is a non-negative integer. In this case, we would say that it's 2 squared, or 4. All right, so simple, direct application of this theorem up above. Now, this kind of, as I said, this is an extremely simple theorem, but it's it's one that obviously you can use to build out analytic limit evaluations for more complex functions. All right. Next, another theorem. So in this one, let's go ahead and write this one out. This is what we're going to, what we'll start doing next is combining functions with known limits. Okay, so let's go ahead and write this out. Let b and c be real numbers. I'm just going to write it like this. B and C are numbers in the real number system in R. And we'll let n be a positive integer. Okay. Then we'll also let f and g be functions with the following limits. So we'll say that the limit of, as x approaches c, of f of x is equal to L, and the limit as x approaches c of g of x is equal to some other value k. Maybe k and L are the same, maybe they're different. So now notice both functions are have the same limit point, right? In both cases, we're approaching the same c on the x-axis, but these two functions may have different actual limits, right? One's L, one's K. Now again, L and K could be the same number, but in general they're not. Okay, so given this wind-up, given the setup, let's see what we're able to show, what we're able to say. And there's a handful, a bunch of these here, and we'll just I'll just write them all down to start with. So the first thing we can say is that the limit as x approaches c of b times f of x, okay, so that's a constant value b multiplied times the function, that's going to be equal to b times L. I'll put the multiplication symbol in there, b times L. So whatever the limit of f is, the limit of b times f is going to be b times that limit. Okay, so this would be useful in the case of like a polynomial where you can factor out a constant. All right. Example 2, or item 2. So remember, this is all the theorem. These are the consequences of our assumptions that b and c are real numbers, and n is a positive integer, and f and g have limits L and K. All right, so the next one is the limit as x approaches c of f of x plus or minus g of x. Okay, adding or subtracting the functions will result in limits that are plus or minus one another. Okay, so if it's f of x plus g of x, then that limit is L plus k. If it's f of x minus g of x, then that limit is L minus k. Okay, very nice. Okay, so you can see already we're sort of building up the machinery to look at polynomials. Okay, let's talk about the ratio. What does that look like? Okay, so the product first. If it's f of x times g of x, then the limits are nicely the product. It may not be obvious why that's the case, but that is the way it works. Then the ratio is there as well. The limit as x approaches c of f of x divided by g of x is equal to L over k. Now, provided that k is not equal to 0, right? So if the limit of g is 0, then the limit of the ratio of f over g is not necessarily defined, right? This doesn't hold in the case of k equals 0. All right, and then the last item in this very nice theorem is that the limit as x approaches c of f of x, and then raise that function to the nth power, well, that's just equal to the limit raised to the nth power. Okay. All right, so what we're going to do next then is we're going to just take this theorem and do a lot of examples, do a bunch of examples. Well, actually, maybe we'll just do a couple of examples to start with, but we'll get into examples maybe in the second video. So let's do an example here. Here's a nice one that makes use of a lot of this. So evaluate. So we want to evaluate the limit as x approaches 2 of 4x squared plus 3. Okay. So what I'm going to do is kind of take the most extreme, I'm going to show as many steps as possible just so that the derivation is very clear. Now in practice, you'll get much faster and you won't have to explicitly show everything, but what you could do, for example, here would be to say that, okay, the limit as x approaches 2 of 4x squared plus 3. Well, first of all, you can break that apart, right? We know that, so there's a definite limit here. There's a definite limit there. We can break these two apart into this. Okay, and further, we can break this term, this piece of it apart here as well. So this would be 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. Okay, so the first piece here would be like the consequence of item 1 up here, right? So a constant times a function. So 4x squared would be like 4 the constant, function's x squared, you pull it apart. And then, of course, this piece here would be a consequence of the prior theorem, so we would be able to evaluate those limits. And so what we can see is that this is going to be 4 times, now the limit here is going to just be 2 squared, right? Okay, and then plus, now what's the limit here? Well, it's going to be 3. All right, so the limit of a constant is the constant. And so you can see that this would be 4 times 4 plus 3. So it would be 16 plus 3, which is 19. Okay. So this polynomial has a limit of 19. Okay. So this is this, for people who recollect their pre-calc or their algebra, this is a polynomial. Right, so this is an example of a second degree polynomial. Now it turns out that limits are very friendly to polynomials, mostly due to the continuity of the polynomial. So let's throw out a theorem here quickly regarding that. So if p is a polynomial function, all right, and c is a real number, all right, then the limit as x approaches c of p of x is equal to, what do you think? P of c. Right, so for polynomials, limits are always equivalent to the value of the function at the limit point, evaluate at the limit point. So that is a very nice feature. For people who recall their pre-calculus, you may remember that the next class of functions that you come across would be the rational functions. And it turns out that we have a nice theorem for that as well. So if r is a rational function, okay, and maybe we say it's given by r of x equals p of x over q of x. Okay, now remember, rational functions are functions where the numerator and denominator are both polynomials, right? So this is a polynomial, that's a polynomial. Then you may be able to anticipate what the conclusion here is if you think back to what we saw in the previous 5-part theorem. You know, when you take the ratio of two functions, the limit is going to be the ratio of the limits. So this would be something real similar, right? So here we would say, so if r is a rational function given by this, and I guess we should say c is a real number naturally, then the limit as x approaches c of r of x, well, it's just going to be equal to r of c, which, because of how we've defined r here, that's going to be p of c over q of c. And so basically you evaluate the rational function at c as well. So rational functions, because they're built on ratios of polynomials, then nicely, conveniently, we can say that that rational functions, the limit is always equal to the function evaluated at the limit point. Let's see an example. Let's evaluate the limit as x goes to 1 of the following, so it'll be x squared plus x plus 2 over x plus 1. Right, so a nice rational function here. Now we know that, well, look, polynomial is a rational function. The previous theorem says the limit is basically the evaluation of the function at the limit point. So the limit here is going to be equal to, well, it's 1 squared plus 1 plus 2 over 1 plus 1. And I think when you plug all that in, you get what? 1 plus 1 plus, so 4 up top, 2 on the bottom. There you go. So the limit there is 2. Couldn't be easier, right? Okay. So important to keep in mind here, what this is saying is that the behavior of the function as we get infinitely close to x equals 1 is that the value gets infinitely close to 2, right? It turns out that in the case of rational functions and polynomial functions, the actual value and the limit are coincident. So, you know, seems kind of like the trivial case, and it sort of is. It sort of is the case where limits are less interesting, but it's important that we know how limits operate under all conditions. And so we'll certainly get into the cases where limits are more interesting, but, you know, this is a good place to start, since many functions involve are polynomials or rational functions, or the combination of those two things with the first theorem that we looked at. Here's another one, similar theorem here. So we'll say let n be a positive integer. Then let's see, the following limit is valid for all c if n is odd and is valid for c greater than 0 if n is even. Okay, so probably you're expecting some square root stuff here, right? And you would be correct. So for a positive integer n, the following limit is valid for all c if n is odd, and is valid for c greater than 0 if n is even. And it is this: the limit as x goes to c of the nth root of x, okay, is equal to the nth root of c. All right, so now what are these? Does this make sense? What are these restrictions? Well, if n is odd, well, let's start with the easier case. If n is even, then you're taking a square root or a fourth root, or something like that. So an even root. In that case, the specification is that c be greater than 0, so z needs to be positive. Of course, you can't take the square root of a negative number, right? That's the idea, and have the result be a real number, right? So the limits, remember, is defined on real numbers, right? So if n is like 2 or 4 or 6, then c has to be positive in order for this theorem to hold. Now, if n is an odd number, like, trivially the first root of x, or the third root, then negative numbers are fine. You can take the cube root of a negative number and have it be a real number. That's not a problem, right? So hopefully that's clear. These kind of a bit of a wind up here, but it should be obvious why that's the case if n and if n is even and n is odd. So okay, so let's do a simple example. Let's find the limit as x approaches 2 of just the square root of x. Well, so 2 is an even number. Oh, sorry, square root is an even number, so this would be the second root, right? So it's an even number, so this is true for all c. And so this would just be the square root of 2. What about the limit as x goes to -1 of the third root of x? Does the theorem work here? It does, right? So because 3 is an odd number, any limit point is true. So this would be the cubed root of -1, which is a real number. Okay. Oh, sorry, off this page there. All right, so that's 2 examples of this theorem in application. All right, very good. I'm kind of tearing through this. That's good. There's a lot of material in this section. This is kind of getting a lot of the limit of the analytic limit stuff kind of out in front. So here's another example. This is going to involve the composition of functions. This one's a little bit more complex. Here's another theorem, not an example. So if f and g are functions such that the limit as x approaches L, okay, sorry, one second, x approaches L of f of x equals f of L, and the limit as x approaches c of g of x equals L, then the limit as x approaches c of the composition f of g of x is going to be equal to f times, f evaluated at the limit of the g function, which of course will be f of L. Right, so this is a more complicated situation here. So if the limit of the interior function is equal to L, right, that's the g function here. So if the limit of the interior function is equal to L, and the limit of the exterior function, that's the f here, is equal to f of L, okay, as x approaches L, then we may move the limit into the composition. Okay, so let me say that again. If the limit of the interior function g here is equal to L, right, as x approaches some point c, and the limit of the exterior function of f of L as x approaches L, then we may move the limit inside the composition. Okay, so let's take a look at this. Let's take a look at an example, kind of get this a little more clearly articulated here. So let's look at, consider this, the limit as x approaches 0 of x squared plus 4. Okay, so we know what that is. We know that that's equal to 0 squared plus 4, so it's equal to 4. Okay, so consider that, and the limit of, as x approaches 4, of the square root of x, we know is equal to 2, right? So you got these two pieces. Okay, so then it follows that the limit as x approaches 0 of the square root of x squared plus 4 is equal to the square root of the limit as x approaches 0 of x squared plus 4. Okay, which is equal to what? Well, so you can kind of evaluate this. So you can say, well, the limit as x approaches 0 of x squared plus 4 we know is 4. Right, and then the square root of that is equal to 2. Okay, so the idea here is if you have a function like this, which is a composition of functions, and you can pull them apart and separately look at them, and you're able to say, first of all, that the first one has a limit L, and that the second one, the limit as x approaches L is just the function evaluated at L, then it's a straightforward thing to move the limit inside of the sort of exterior function, in this case the square root. Right? So this step here is kind of the novel thing here in this theorem. Right? That's the nice feature. All right. Let's look at another theorem, and we'll come back to this concept here in a few. But let's throw another couple theorems out into the mix, and then what we'll start to do is kind of combine all of these things. There's just a lot of ground to cover ahead of that. Okay, so let's go ahead. This is going to be all of the trig functions and the natural log and the those types of things. So let's go ahead and let C be a real number in the domain of the given function. Then, all right, so a whole bunch of these here. So start with this, the sine. The limit as x approaches c of the sine of x is equal to the sine of c. Okay, same thing for the cosine. Okay, so that's nice. So the cosine and sine, it's true for the tangent, cotangent, secant, and cosecant as well. So I'm just gonna, in the interest of thoroughness, I'm gonna write them all out. Limit as x approaches c of the tangent of x is equal to the tangent of c. The limit as x approaches c of the cotangent of x is equal to the cotangent of c. The limit as x approaches c of the secant is equal to the secant evaluated at c. And finally, the last one would be the cosecant. The limit as x approaches c of the cosecant of x is equal to the cosecant of c. Okay, so we get all of the trig functions. They come very, very nicely. A couple other ones here that are what you can lump in with this same, basically c being a real number in the domain of the function. We could also say that the limit as x approaches c of a to the x power. All right, so a with the variable in the x up in the exponent is equal to a to the c as well. And then finally, the natural log. So the limit as x approaches c of the natural log of x is the natural log of c. So these are all continuous functions. We'll get into continuity probably in the next lecture. I have to be sure about that. But continuity is what makes all of these functions that we're looking at work so nicely with limits. Right? So when a function is continuous, which we'll get into what that means later, they have very predictable and nice limits. It's only when functions start to behave strangely and have strange properties that, strange properties with respect to continuity, that the function's limits start to deviate from the evaluation of the function. Let's do some examples here. And here's where we'll start to combine some of our previous stuff here. So let's say the limit as x approaches pi of the function x times the cosine of x. Okay, so we want to evaluate this function or this limit. So we would say what limit as x approaches pi of x cos x. Well, we've got a product of functions here. You've got the x times the cosine of x. Both of those individually have established limits, so we can think about them like this. You can think about it as a product. You don't necessarily have to write it, but just to be explicit, I'm going to write it. You can think about it like that. They're both going to have separate limits, and we can evaluate them separately. So we know, of course, the limit of as x approaches pi of x is just pi. And what's this one? Well, it's cosine of pi, right? We just saw that. Okay, so it's just pi cos pi. All right. So that's going to, obviously that's using the trig. It's also using the identity function limit. It's also using the fact that you have a product of functions you can pull apart and kind of think of separately. Another example would be the limit as x approaches e. So this would be the exponential of the natural log of x cubed. Okay, so what does this limit look like? Well, so this guy, let's talk about this. So this one, so again, just lots of experience is helpful here. So limit as x approaches e of the natural log of x cubed. Well, if you recall, the natural log of x to the n is equal to n times the natural log of x, right? So you can pull this apart a bit. Right, you get something like this. Right, so we've seen this in the algebra courses. And then, of course, you can pull the 3 out. And you get this. And we know, we just talked about what the natural log, what the limit of the natural log function is, right? And so we know that this is going to be equal to 3 times the limit as x approaches e of natural log of x would be just the natural log of e, which is 1. Okay, so these are so in a function like this, which isn't really obvious that the value of the limit is 3, well, you can kind of go through and kind of piece by piece pull it apart using properties of logarithms, properties of limits, and then of course the fact that natural log of e is 1. Here's another example. This one's a bit more of a left field kind of example, but you've got, what about the limit as x goes to 0 of the tangent of x divided by a polynomial x squared plus 1. All right, so you could think of this as like an f of x over a g of x, right? So we're going to pull that theorem in here that basically breaks the ratio into 2 separate limits. And so we could say this would be equal to, because both of these are understood to have a limit, the limit as x approaches 0 of the tangent of x divided by the limit as x approaches 0 of x squared plus 1. And so what do we get? Well, we can evaluate these separately. We get tangent of 0 divided by 0 squared plus 1. And the tangent of 0, right, so that's going to be 0. Okay, and so it'd be sine over cos, so it'd be 0. And this would be, of course, 1. So we get 0 is the limit of this function as x goes to the value of 0. All right, very good. Let's see. So that was a bunch of examples. So we did tear through a lot of examples. Now, what I really recommend people do, if you're taking this course, is go find yourself a calculus book and start doing lots of examples of these kinds of limit evaluations. It starts to kind of feel like a new kind of algebra a little bit, or algebra with some new features. And as you know, when you're learning algebra, the thing to do is to do lots of algebra. That's the way to learn these things. So this is a lot of the theorems that we'll need to evaluate limits analytically, but we'll get into some more. Here's another one. And so this one, this is a little bit more complex as well. relative to some of the ones we've looked at. So let's let C be a real number. And let f of x equal g of x for all x that are not equal to c in an open interval containing c. Okay. So what's the idea here? Well, the idea is that you've got two functions, f and g. They're basically everywhere equivalent except at a real number c, right? And so then what we can say is that if the limit of g exists at c, then the limit of f also exists at c. And to be more specifically, to be more specific, probably should have just said this to begin with, the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. Okay, so basically what this is saying is if you have two functions that are identical everywhere except for at a value x equals c, then the limit at c is going to be the same for them irregardless of what the other function, what the two functions, how the two functions differ at that point. So let's see a picture, like a nice picture here will make this totally clear if it isn't. Right, so let's say we've got, okay, so we've got this function g of x. Right, let's just make it simple here and say that g of x is like the identity function. Now g of x is defined at c. So your x-axis, your y-axis, and your function g. So g is defined at c. And let's say right on top of it, except I'm going to draw it on a separate graph, but you can imagine these two as being like right on top of each other. Let's say you have another function f, which looks almost exactly the same, except a hole at c. Well, so what the theorem is basically saying is that whatever the limit as x approaches c of g of x is, well, then the limit as x approaches c of f of x is the same. They're equal. Okay. Now, it's very obvious in the case of like a straight line like this that would be true. But keep in mind this works for functions that are arbitrarily crazy as long as the limit exists and the functions overlap each other sufficiently on an open interval around c. So there has to be some space around c for which both functions agree and are identical. All right. So let me see if I can draw like slightly more complicated example here. So let's say this is your c function or your g function here. Okay, and here's c. And so clearly the function has a limit at c. So then let's say that the f function does something different. Let's say it kind of goes like this. Coincident here, except there's a hole, and then it moves away like this. Right, so it's a little difficult to see which one is which, but I'll try to make the f a little heavier. Right, but so in that case, you can see that the functions aren't identical, but they are equivalent on an open interval around c, and so the limit of the one is the limit of the other. Right, so in this case, the limit of g is equal to the limit of f as x approaches c. Okay, so a handy theorem. So this is I think, you know, this is a really easy example of the theorem. It's obvious, really, that the limit must be the same value since the two functions are identical at every point except for c. But notice it works even for functions that aren't identical at every point, just so long as they're identical on some arbitrarily small open interval around the limit point C. It doesn't say the interval has to be a certain size or anything, it's just some open interval. Okay, and so it can be a powerful function. Let's take a look at an example. So let's take a look at an example here. Let's evaluate the limit as x approaches 1 of x cubed minus 1 over x minus 1. All right. Let's take a look. Let's tear this apart a little bit. So notice here the problem is that we can't just straight evaluate this, right? Because this is a polynomial. Sure, you should just be able to plug in 1, but you can't divide by 0, right? Okay, so the fact that you have a denominator here means that you can't blindly apply that because g of c would be equal to 0. Right, so you got a problem. So what can we do? Can we do something with this? Well, let's take a look at this function a little closer. So x cubed minus 1 over x minus 1. All right, so we can do some, we can expand this top piece here. So we can expand the x cubed minus 1, and specifically we can write it like this: x minus 1 times x squared plus x plus 1 over x minus 1. Okay. Now notice that this is equal to the limit as x approaches 1. Now what happens here? Well, those will cancel, and you get x squared plus x plus 1. Now, if you think of g of x as being this function and f of x as being this function, so if you think of it in this way, right, g of x, so f of x is the original function that has like this hole at x equals 1. But what you can see is that, well, essentially, we can basically take this function f of x here and we can expand it, and then we can do some cancellations, and we see that the two functions, f and g, are equivalent everywhere except for x equals 1. So naturally, obviously, if this function is equal to that, which is equal to that, then the functions are the same, right? Except this one has this hole in the domain, right? So this is the direct application of this previous theorem. So yeah, we can see that g of x and f of x will agree at basically all values of x except for x equals 1. For all x except x equals 1, right? Where the hole is, where the denominator would be 0 in f. Right, and so that being the case, what we can say is the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of g of x, okay, which obviously is what we just calculated, which is equal to the limit as x approaches 1 of what? X squared plus x plus 1, which is just a polynomial, right? So you could say, what, 1 squared plus 1 plus 1, so that's 3. And so if the two functions f and g differ at only that one point, then they have the same limit at that point. Okay, so this is a really nice application of that theorem. Now the thing to keep in mind, you always have to be a little bit careful with limits, and this is something that kind of drove me crazy when I was an undergrad, and I expect it will drive you crazy too. When you see a function like this, you may think to yourself, well, this is just a straight application, just plug in 1 and then, oh, I get a 0, so the limit doesn't exist. The limit does exist. This is a rational function. It's everywhere continuous except for maybe at that one spot. And so how to figure out what the value of the limit is at that one spot? Well, you may be able to do some algebraic manipulations to derive an equivalent function, a function that's everywhere equivalent except maybe at that one spot, x equals 1. So you have to be careful. If it's a rational function, it should have a limit. It just may be harder to find. Okay, very good. Very good. So that was a nice example. Let's do kind of a summary here. How to evaluate limits, a strategy. Okay, so this is kind of a summary because we did touch on a lot of things here. So the first thing would be to, obviously make note of what we just talked about, right? Learn which limits can be evaluated by direct substitution. And that would be the approach to take, naturally, if it's doable. Learn which limits can be evaluated by direct substitution. Okay. So that would be things like your polynomials and your trig functions and your constant functions and things like that. Rational functions for many cases. If you cannot use direct substitution, try to identify a function g of x that's equal to f of x everywhere except the limit point, kind of like the previous example. So what we'll say is if you cannot use direct substitution, okay, try to identify a g of x equals f of x, right? So g being the function you try to identify for all x not equal to c, and then use the previous theorem. So what that basically kind of boils down to is, can you transform the function in some way such that you get rid of the issue at the limit point, right? So if it's an issue where you're dividing by 0, for example, it's the most common one probably. Can you transform the function such that you get rid of the dividing by 0 at the limit point problem? And then you can likely use direct substitution. And then the third strategy would be, if this kind of all breaks or none of these things work, you could use graphs or visualizations or tables of values to identify the limit numerically. Use graphs or tables, and I would say really use the graphs or tables to reinforce or aid your intuition. Okay, right, so that has been that's kind of a strategy, for sort of a 3-point strategy for evaluating limits analytically, right? So if you can, just evaluate it directly. That's your best option, simplest option, obviously. If that's not possible because there's some issue with the denominator or some domain issue, see if you can transform the function, or i.e. identify a g of x that's similar to f of x, or identical to f of x on the open interval around the limit point c. And if that doesn't work, also use graphs or tables to help reinforce or aid your intuition. So with that, I'm gonna go ahead and end this video. There'll be a part 2, part B to this lecture we'll go into more examples and have more things to talk about with evaluating limits analytically.